In the stillness between galaxies, where the universe cools into silence, a faint glow stretches across the cosmic sky. It is older than every star, older than every atom, a surviving whisper from the moment the universe first learned how to exist. This soft radiation, the cosmic microwave background, drifts like ancient dust, a pale afterimage left behind by a newborn cosmos. It is quiet, uniform, unassuming, a relic that has watched 13.8 billion years pass without ever raising its voice. Yet within this near-perfect calm, something begins to tremble across its mottled patterns of temperature and light. Fluctuations no wider than a hand on the sky start to reveal the slightest traces of order. Shapes that once seemed random begin to stretch, to align, as though pressed from beneath by an unseen hand. The universe's oldest light, long thought to be nothing more than cooling debris from the Big Bang, begins to pulse with a rhythm too delicate to dismiss. For decades, cosmologists treated these tiny variations as statistical noise, natural wrinkles in an expanding cosmos. But now the wrinkles shift. Now they form the faintest outline of something buried deeper than the CMB itself, something hidden behind its comforting veil of static. 13 billion years of cosmic silence thin into transparency. And from behind the glow, a subtle imprint emerges, a signature older than the galaxies, older than the first stars, older even than the space that contains them. It does not shine. It does not move, but its presence presses outward, as though waking from an age-long sleep, in the dim light of the universe's first memory. Something ancient has begun to stir, and the cosmos is no longer as quiet as it once seemed. The story of the hidden imprint begins, as many great scientific revelations do, with an accident. In 1964, on a quiet patch of land in Homedale, New Jersey, a pair of radio astronomers attempted to measure signals from distant galaxies. Arno Penzias and Robert Wilson worked with a massive horn-shaped antenna left over from a satellite communication experiment, an instrument far more sensitive than they needed. Their goal was simple: clean the data, remove the noise, and listen to the universe with as much clarity as human engineering could allow. But the noise would not go away. It droned in every direction, a persistent hiss that clung to the sky itself. The two scientists cleaned the antenna, recalibrated the electronics, and chased away a pair of pigeons nesting inside the instrument, hoping the birds and the layer of debris they had left behind were to blame. Yet even after every earthly source of contamination was removed, the hiss remained. It was faint but stubborn, uniform across the heavens, behaving like no known astronomical signal. Only later did Penzias and Wilson learn that theorists had predicted such a sound years earlier, the cooled remnant of the Big Bang. Almost by accident, they had uncovered the oldest fossil of the cosmos, the cosmic microwave background. When the CMB was announced to the world, it reshaped cosmology in an instant. No longer was the early universe a hypothetical stage dismissed to mathematics and speculation. It was now an observable fact, mapped across the sky in soft, microwave light. What had once been a theoretical afterglow had become a real, measurable imprint of creation. Early cosmologists studied this glow with wide eyes. In its near-perfect uniformity, they saw the quiet symmetry of a newly born universe, still cooling from its primordial fire. But within its small, delicate variations, temperature differences measured in fractions of a degree, they recognized the seeds of everything that would follow: the first gravitational wells, the earliest clustering of matter, the faint hints of galaxies yet unborn. For years, the CMB remained a simple map of cosmic infancy. Its resolution was limited, its details blurry, its features too coarse to uncover deeper secrets. But the questions it raised lingered. Was the early universe truly uniform? What mysteries lay hidden beneath the soft haze of microwave light? And what structures, visible or invisible, might have left an imprint on this ancient canvas? By the late 1980s, humanity was ready to look again, this time with clearer eyes. In 1989, NASA launched COBE, the Cosmic Background Explorer. COBE did more than confirm the CMB's existence. It revealed the first detailed map of its temperature fluctuations. For the first time, the ancient afterglow displayed structure, patterns of slightly hotter and colder regions that match predictions of cosmic inflation. These were the fingerprints of the earliest matter distribution, captured in the universe's cosmic cradle. A decade later, WMAP sharpened the view. Its data revealed the universe's age, its composition of dark matter and dark energy, and the shape of space itself. The CMB became a tool for decoding everything from the geometry of the cosmos to the density of primordial plasma, but the deepest revelation came in 2009 when ESA launched the Planck satellite. Planck produced the sharpest CMB map in human history, a tapestry of exquisite detail stretching across the entire sky. It was here, in these unprecedented measurements, that something unusual began to whisper through the noise. The anomaly did not arrive as a bold feature, nor as an obvious signal. Instead, it was a subtle, almost fragile pattern concealed beneath the standard temperature fluctuations, far too faint to see with a casual glance. It only appeared when the data was filtered with a particular mathematical lens, isolating extremely low-frequency modes. Under this scrutiny, a large-scale shadow or coherent region seemed to press through the map, extending far beyond the scale predicted by inflation. It was dismissed at first. Artifacts like this often arise from instrument heat, calibration drift, or even the scanning strategy of the satellite. Many scientists shrugged and marked it down as yet another statistical fluke, destined to vanish once the data was cleaned more carefully. But it did not vanish. Even after foreground emissions were removed, dust from the Milky Way, synchrotron radiation, cosmic rays, the anomaly remained. It reappeared when the analysis was repeated with different masks, different algorithms, different statistical models. When the Planck data was cross-referenced with WMAP, the faint imprint persisted, as though etched into the sky itself. Still, skepticism remained. Cosmologists are trained to distrust patterns that appear only under specific filters. The universe, after all, produces coincidences. Random fields can mimic structure. Observers can be misled by subtle biases in analysis. And yet, the persistence of the feature unsettled those who reviewed it closely. A small group of researchers from institutions across Europe and North America began to examine the anomaly with greater resolve. They compared power spectra, studied the alignment of temperature gradients, and evaluated the coherence of the structure under simulations. With each layer of analysis, their caution deepened. Something about the pattern defied the expected distribution of cosmic variance. It was too large, too structured, too consistent. The team released a paper outlining the anomaly, careful, technical, unwilling to draw cosmic conclusions. They spoke of low multipole power suppression, hemispherical asymmetry, unexplained alignments. The scientific language was meticulous, restrained, but between the lines ran a quiet unease. Something in the data was not obeying the rules. The response from the broader community was measured, if not dismissive. Some argued that the anomaly reflected our position in the galaxy. Others suggested unaccounted systematic errors. Many reminded their colleagues that statistical outliers were inevitable in datasets of cosmic scale, but even among skeptics, a quiet curiosity began to grow. If the anomaly were merely noise, it should behave like noise, random, inconsistent, vanishing under corrective models. Instead, it remained steady, faint but unmistakable. Like a distant ripple against the fabric of space-time, the small team continued its work. New hints emerged. Polarization maps showed the anomaly's faint influence. Lensing reconstructions revealed an unusual distortion. And the structure appeared, impossibly, to have depth, as though rising from behind the CMB rather than within it. It was still too early to claim a discovery. Too early to declare the universe stranger than expected. But in the cold glow of the cosmic background, where silence had reigned for nearly 14 billion years, a whisper had emerged, a whisper that refused to disappear. What began as an accident in 1964 had become the first clue. What appeared as noise in Planck's data had become a suspicion. And in the hands of the careful few who dared to look closer, the suspicion was slowly transforming into a question that the universe itself might struggle to answer. The anomaly first appeared as little more than a pale disturbance on the horizon of understanding. a whisper folded into the glow of the cosmic microwave background. Yet as the data sharpened and the analyses deepened, something unsettling took shape. What had once been dismissed as a trivial irregularity began to reveal a quiet defiance, a pattern whose very existence pressed against the limits of cosmology. The first sign of trouble was its coherence. Random noise leaves no signature, no structure, no rhythm. It scatters like dust, indifferent to direction or scale. But this anomaly behaved differently. It stretched smoothly across vast regions of the sky, its features aligned with a persistence that statistical chance could not easily mimic. It formed gradients where none should form, contours where only randomness was expected. In the algorithms that filtered it from the cosmic glow, it emerged with an almost deliberate calm, too ordered, too stable, too patient to be dismissed. Its size deepened the unease. The anomaly spanned an enormous portion of the celestial sphere, reaching across scales larger than inflationary theory comfortably allowed. According to the standard model of cosmology, the early universe expanded so rapidly that no regions now separated by billions of light years could have communicated with one another. Temperature variations on these giant scales should therefore be random, disconnected, incapable of forming a unified structure. Yet the anomaly acted as if it had cohered across a region, larger than inflation would permit, as if vast stretches of the early universe had been connected long before the laws of modern physics claim they could have been. It was a violation not of a minor equation, but of the very principle of cosmic homogeneity, the idea that, on large scales, the universe is smooth, symmetric, and unpatterned. Even stranger was its apparent depth. Most CMB features lie on a two-dimensional surface, the surface of last scattering, a kind of ancient photosphere where photons were finally freed from the early plasma. But when researchers modeled how the anomaly interacted with gravitational lensing, a subtle distortion emerged. It behaved not as a flattened imprint on the CMB, but as if it existed behind that ancient wall of light, rising faintly through it like the shadow of something enormous concealed behind a thin curtain. This was not behavior typical of known structures or cosmic foregrounds. Galactic dust emits at different frequencies. Distant clusters distort light through gravity. Even primordial waves leave their marks in predictable ways. But none of these could explain a feature that seemed to press outward from beyond the boundary of observable time. And if anything sat behind that boundary, it meant it existed before the visible universe began. A presence older than the CMB. A structure predating the recombination era. A signal crossing through the horizon of the Big Bang itself. Such implications struck directly at the foundations of cosmology. The standard model rests on the assumption that the Big Bang marks the beginning of the observable universe, not simply an event in time, but the origin of time itself. The CMB is not merely ancient light. It is the earliest possible light, a limit beyond which photons cannot carry information. If a pattern seemed to emerge from behind that surface, then either the model was incomplete, or the cosmos was revealing a domain previously inaccessible to physics. For many researchers, this notion carried an unmistakable tension. It suggested a universe larger than the one described by textbooks, richer than the simple narrative of expansion and cooling, stranger than the steady mathematics of inflation. It implied that cosmic history might not begin with a single horizon, and that the visible universe might not be the totality of space, but merely a window into a deeper, unseen expanse. Such possibilities triggered both fascination and discomfort. In scientific discussions, the tone grew cautious. Cosmologists who spent their careers refining the standard model now faced the unsettling possibility that the early universe carried scars from an earlier epoch, traces of a boundary, a collision, or a structure beyond conventional comprehension. The anomaly became a kind of intellectual tremor, small, silent, but profoundly destabilizing. What unsettled researchers further was the pattern's behavior across different wavelengths. NASA's WMAP data showed the anomaly. ESA's Planck data showed it again. Even earlier and noisier observations hinted faintly at the same shape, different instruments, different noise levels, different scanning strategies. Yet the pattern resurfaced each time, its edges sharpening as measurement techniques improved. When physicists filtered the sky by frequency, the anomaly's presence changed subtly but did not disappear. It did not behave like galactic dust or synchrotron emission, which falls away predictably at specific wavelengths. Instead, it persisted across microwave bands, sometimes faint, sometimes bold, as if anchored not to the instruments but to the universe itself. This cross-frequency consistency was one of the most troubling features. Foreground signals typically peak in certain bands. Instrumental noise follows known distributions. But a true cosmological imprint, something woven into the geometry of space-time, would appear across all wavelengths as a coherent structure. The anomaly behaved exactly in that manner. Still, the community hesitated. Extraordinary claims require extraordinary evidence, and no one wished to mistake an artifact for a revelation. But as the results continued to resist explanation, the tension grew. Could a cold spot, a supervoid, or an unmodeled foreground produce such coherence? Simulations showed that chance alignments were possible, but exceedingly rare. Foregrounds could introduce structure, but not with this level of stability. Even statistical anomalies, the ever-present specter in cosmological data, struggled to defend the scale and depth now observed that a few theorists began to whisper more daring ideas. If the anomaly came from behind the CMB, then perhaps the Big Bang was not the ultimate horizon, but a transitional layer. Perhaps the universe had undergone cycles, each leaving faint residues imprinted on the next. Others speculated about collisions with neighboring bubble universes or interactions with topological defects formed in the earliest fractions of cosmic time. Some wondered if unknown quantum fields might have survived inflation, leaving behind a low-frequency modulation that still rippled through space-time. None of these theories were embraced with certainty, but their very necessity revealed the gravity of the situation. If standard cosmology remained untouched, the anomaly had no place. If the anomaly remained real, cosmology needed new chapters. The shock was not explosive. It unfolded slowly, quietly, in conference rooms and research papers, in late-night discussions between scientists tracing the edges of the unknown. Most of the cosmos remained beautifully predictable, elegantly described by decades of theoretical work. But at its farthest boundary, in the dim glow of the oldest light, something refused to fit. As though the universe were hinting at a story older than the Big Bang, older than cosmic inflation, older than the canvas on which the CMB was painted. For now, it is only a whisper, a faint signature, a suggestion that the universe may contain more layers than previously imagined. But in the world of cosmology, even a whisper can shake the foundations of understanding. And this one, emerging gently from behind the cosmic background, carried the unmistakable weight of something ancient waking into view, something that should not exist, and yet, undeniably, does.
As the anomaly refused to fade, astrophysicists turned to the one resource capable of speaking across cosmic time: data. Not new data at first, but old maps revisited with new eyes, new mathematics, and new suspicion. The cosmic microwave background had been studied for decades, but now its familiar landscape became a labyrinth, each pixel a potential clue. Teams across the world began reprocessing the sky, peeling back layers of noise and foreground contamination with statistical tools more advanced than anything available when the first maps were made. The earliest step was to abandon traditional filtering. Standard cosmological analysis assumes that the CMB's temperature fluctuations follow nearly perfect Gaussian statistics, random, symmetric, and lacking preferred direction. But when researchers applied alternative statistical frameworks designed to capture faint correlations across enormous scales, the anomaly sharpened. Wavelet transforms, spherical harmonics, and non-Gaussian estimators were tested in succession. Each method, despite approaching the sky from a different mathematical angle, highlighted the same structure. In these refined maps, the anomaly no longer appeared as a diffuse smear. It gathered shape. It developed edges. And most disturbingly, It began to influence polarization, the delicate patterns that describe how ancient photons twist and spin as they move through space. To cosmologists, polarization is the CMB's hidden diary. E-mode polarization reveals density fluctuations in the early plasma, while B-mode polarization carries the faint fingerprints of gravitational waves. Both are extraordinarily subtle, requiring instruments of exceptional sensitivity. Yet when the anomaly was superimposed onto these polarization layers, a quiet shift emerged. The E-modes bent slightly around it, as though the structure altered the orientation of ancient light. The B-modes, expected to be nearly absent on large scales, showed faint disturbances out of line with inflationary predictions. These distortions were small, almost delicate, but they were coherent. They traced the same contour that temperature anomalies had suggested. No known foreground, from galactic dust to cosmic synchrotron radiation, behaved in this synchronized way. Something was affecting all three channels, temperature, E-mode, and B-mode, as though exerting a subtle gravitational pull. This suspicion led to the next step: gravitational lensing reconstruction. The CMB does not simply pass through space. It is bent, twisted, and sheared by the gravitational fields of galaxy clusters, dark matter webs, and large-scale cosmic flows. By analyzing these distortions, researchers can rebuild a map of the invisible scaffolding of the universe. Yet the anomaly behaved strangely under lensing reconstruction. Where gravitational fields should bend light smoothly, the reconstructed flow appeared to warp subtly around the anomaly's position. It was as if the anomaly were exerting a gravitational influence inconsistent with any known structure, not a void, not a cluster, not a filament of dark matter. It behaved as though something massive, or perhaps something fundamentally different, lay beneath or beyond the last scattering surface, bending trajectories from a depth humans were not supposed to peer into. This gravitational irregularity drew attention from quantum field theorists, who analyzed the CMB for signs of primordial field fluctuations. If inflation had produced quantum noise that stretched to cosmic sizes, it would imprint low-frequency modulations on the sky. But when researchers examined the anomaly within this framework, they found something discordant, a modulation far too smooth, far too controlled. Quantum field simulations showed that standard inflation should produce random fluctuations across large scales. Yet the anomaly exhibited a persistent low-frequency ripple, gentle, almost rhythmic, that repeated across several independent analyses. It was not noise. It was not random. And it was not predicted by any inflationary model. Machine learning offered a new path. Teams fed supercomputers millions of cosmological simulations, universes with different inflation speeds, different densities, different dark energy parameters, even exotic early universe conditions such as topological defects and primordial magnetic fields. The models learned to detect anomalies, categorize them, and reproduce them under varied physical assumptions. But no matter how the simulations were trained, no matter how parameters were stretched or deformed, the anomaly never appeared naturally. Models could replicate cold spots, alignments, or statistical oddities, but not this signature. The algorithms marked it as an outlier, so rare it lay beyond the scope of physical probability. In some experiments, the models identified the anomaly as an intrusion, something that did not belong to the dataset they were trained on. It was as though the machine learning systems recognized what researchers hesitated to articulate. The anomaly did not resemble a feature of the universe as currently understood. And then came the moment that unsettled even the most cautious scientists. As filtering methods grew more refined, something unexpected occurred. The anomaly's shape changed. Not dramatically, not violently, but subtly, shifting at the margins. In response to the mathematical techniques used to isolate it, it was as if the signature moved under different filters. Not physically, but mathematically, almost as though it interacted with the analysis itself. Each transformation brought out a different aspect. Wavelets emphasized its center. Harmonics emphasized its edges. Machine-trained filters highlighted its gradients. The anomaly behaved not like a fixed pattern on the sky, but like a deeper signal resonating through the CMB, adapting depending on how it was observed. Researchers debated whether this was an artifact of data processing or evidence of a more complex imprint, something encoded not only in the light, but in the underlying fabric that produced it. Skepticism persisted, but caution gave way to curiosity when the Planck mission team revisited their own data. A reanalysis of temperature and polarization maps, conducted nearly a decade after the mission's completion, revealed an unsettling possibility. The anomaly appeared slightly stronger. It was not a dramatic increase, more of a sharpening, a faint intensification of contrast barely above statistical thresholds. Yet it was consistent across multiple bands. The Planck team could not claim it was growing. Cosmic variance, analysis techniques, and noise all blurred the certainty. But the trend existed, and its implications were profound. If the anomaly's imprint had indeed changed over 10 years of observation, then it was not a relic frozen at the edge of time. It was not a static feature imprinted at recombination. It was not a fossil from the first seconds after the Big Bang. It was behaving as though it were active. As if something behind the CMB had shifted or brightened or moved so subtly that only the universe's oldest light could detect it. No cosmologist claimed this publicly. No paper dared phrase the implication directly. But privately, across conferences and quiet conversations, the same thoughts surfaced like a rising tide. If the signature beneath the CMB is changing, then something behind the cosmic background, something older than the visible universe, is no longer entirely still. The investigation had begun as a technical exercise, a re-examination of maps long thought complete. But now it pointed toward a deeper truth, one that hovered at the edge of comprehension. The universe was revealing not just its past, but something stirring within its hidden depths, a quiet movement from beyond the dawn of time. Across decades of observation, a handful of celestial anomalies had lingered at the margins of astrophysics. Cosmic cold spots, hemispheric power asymmetries, regions where temperature dipped against expectation. Each carried its own quiet strangeness. Yet none of them prepared the scientific community for what began to unfold within the filtered maps of the cosmic microwave background. The CMB had always been a soft mosaic of chaos, a random scatter of primordial heat shaped by quantum jitter in the earliest fraction of a second. Its fluctuations were supposed to be formless, stochastic, a statistical soup without intention or direction. But this structure, the one that had begun to surface behind the noise, did not behave like a cold spot or any known remnant of early universe turbulence. Instead, it appeared organized. When processed across multiple frequencies, it acquired shape. When smoothed, it held its boundaries. When the noise model was altered, it shifted in tandem, adapting as though it were etched into space-time itself. Cold spots faded with better data. Noise vanished under new models. But this feature endured, persistent and patient, as if sculpted by something older than the universe's first light. Researchers began by comparing it to the famous WMAP cold spot, a peculiar depression of temperature that some once attributed to a supervoid in the large-scale cosmic web. But the cold spot had an explanation grounded in cosmic structure formation. This new anomaly did not. It wasn't colder in any traditional sense. It wasn't hotter. It was a subtle curvature, a pattern lying beneath the ordinary fluctuations, more like a ghost image hidden in the weave of ancient radiation, and unlike the cold spot, whose dimensions were fixed by cosmic expansion, this structure resisted classification. It spanned a scale far larger than any supervoid, any basin of matter, any remnant of gravitational clustering. It stretched in a way that suggested coherence, beyond the reach of cosmic inflation, a violation of the principle that the universe should look nearly uniform when observed at grandest scales. Something about it felt deliberate, not conscious, not intelligent, but strangely intentional in its geometry, as though shaped by a physical process that standard cosmology had never accounted for. Then came the implication that many had quietly feared: the feature might not be static. Over the course of successive datasets from WMAPs later released to Planck's full mission maps and their reprocessed polarization data, a faint trend began to emerge. The anomaly's amplitude appeared to shift by tenths of a percent. Its contour sharpened in some reconstructions while broadening in others. Individually, these changes lay within the statistical fog. Together, they whispered of something that should have been impossible. Cosmic background radiation is a fossil. It does not evolve on human timescales. It does not shift, pulse, or respond. Yet here, at the edge of detectability, something seemed to move. Like a tide pulling at the limits of the cosmic horizon, astrophysicists combed through every possible systematic source: detector noise, calibration drift, thermal contamination, residual foreground galactic dust. But none of these effects could mimic the coherence seen across independent instruments, detectors, or years of observation. The signal resisted dismissal. Every attempt to wash it away only made it more visible. This led to one of the most unsettling measurements: a subtle, directional alteration of lensing potential, gravitational lensing. The bending of light by mass allows cosmologists to reconstruct the distribution of matter in the universe. And when researchers mapped how the CMB should be distorted by known cosmic structures, the anomaly bent those projections out of alignment. The distortion didn't match any cataloged mass. It didn't correspond to galaxies, voids, or filaments. It acted as though something vast and distant were tugging at spacetime from beyond the observable boundary, a gravitational echo of unimaginable scale. Models attempting to reproduce this gravitational flow kept failing. The anomaly behaved like a shadow cast by something not inside the universe we can see, but pressing against it. Speculation, once avoided, slowly entered the discussion. Some proposed the existence of an ultra-large-scale structure beyond the cosmological horizon, larger than any galaxy cluster. larger than the Laniakea supercluster, larger even than the network of cosmic filaments threading the deep universe. A structure so massive that its gravitational influence extended across the boundary, thought to mark the limit of causal physics. Others invoked the possibility of an adjacent cosmic region, an inflationary bubble with slightly different curvature or density. If the early universe had undergone a phase of rapid expansion, perhaps neighboring regions left faint impressions on one another, friction marks between universes, preserved as thermal signatures within the CMB, and then came theories more radical still, a pre-Big Bang relic, a boundary left by a contracting universe before the bounce, a frozen scar in spacetime imprinted by primordial gravitational waves during their first trembling oscillations, because the anomaly did not simply distort the CMB's temperature map, it seemed to touch its polarization as well. Polarization patterns in the CMB come in two varieties: E modes, the smooth radial signatures, and B modes, the twisting curls that are fingerprints of gravitational waves. The standard model predicted their behavior with exquisite precision. Yet in the vicinity of the anomaly, polarization angles rotated slightly off their expected orientations, as if stirred by a low-frequency ripple no inflationary model could produce. This ripple, faint as breath, seemed to skim across the map with a rhythm that should not exist. It was not noise. It was not foreground contamination. It existed at scales where theoretical models predicted silence. As machine learning systems trained on millions of simulated universes attempted to recreate the anomaly, they failed repeatedly. Even when the simulations were adjusted to exotic parameter ranges, unusual dark energy equations of state, variable inflation rates, hypothetical early universe defects, the signature refused to appear. It remained a singularity in data space, a pattern that machines could detect, but never reproduce. This failure forced researchers to confront a chilling possibility. Perhaps the anomaly was not a byproduct of early universe randomness, but of something external, a relationship, a tension, a force acting upon the cosmic fabric. Throughout the scientific community, responses ranged from fascination to unease. The anomaly touched foundational assumptions, the smoothness of the cosmos, the completeness of inflation, the finality of the Big Bang horizon. If something lay behind the CMB, it meant that the observable universe was not the whole story. It suggested an older landscape, one that existed before the universe as it is known today. But the most unsettling moment came when a Kungman came, when a Duque cross-comparison of Planck's 2013 and 2018 releases revealed a statistically curious trend. When the anomalies region was isolated and analyzed across multiple filtering scales, its significance appeared to grow. Not dramatically, but enough to imply that the underlying structure, whatever it was, had become slightly more pronounced. No physical process within the CMB itself could cause such a change. The radiation was ancient and inert. Its map was a snapshot, frozen at 380,000 years after the Big Bang. Yet here, in the deepest recesses of analysis, something behaved as though it were awakening, not metaphorically, not poetically, but mathematically. A contour sharpened, a gradient deepened, a harmonic pattern gained coherence. Not by much, just enough for the human mind to sense motion, where no motion should be. For the first time, whispers circulated of an evolving feature, a shifting presence behind the cosmic veil. something vast enough to bend light across universes, something patient enough to wait through cosmic epochs, something old enough to predate the first stars. With each refinement of data, the boundary grew clearer, the distortion more confident, the whisper more like a signal. And as the scientific community gathered around the anomaly, a quiet tension settled over the field, the uneasy awareness that whatever lay behind the CMB was no longer merely hidden. It was beginning to emerge. As the anomaly gained definition, the cosmos seemed to open a quiet chamber of possibilities, a room where theory, speculation, and cosmological imagination converged. Within that chamber, scientists began building models to explain what no standard equation could comfortably hold. Each proposal carried its own logic, its own evidence, and its own unsettling implications. And each brushed against the limits of what the universe was ever expected to reveal. The first explanation rose from the vast architecture of inflation itself, the multiverse collision theory. During the earliest fraction of a second, the universe expanded beyond comprehension, an exponential swelling that stretched quantum fluctuations into the seeds of galaxies. But inflation, in many models, did not happen once. It happened in countless regions, each forming its own universe, each ballooning away into a cosmic archipelago of space-time islands. If two such universes brushed against one another during that early expansion, the collision could leave a circular scar, a faint thermal imprint etched into the CMB, detectable billions of years later. Some researchers believed the anomaly resembled such a collision, too large, too coherent, too geometric to be random. But the theory faltered where the data grew strange. A collision scar should be uniform in temperature difference, a smooth disk across the sky. This anomaly was not smooth. It had texture, subtle gradients, faint twisting contours that shifted across polarization maps. Its shape, instead of being a simple stamp, seemed to possess depth, a gradual layering that no inflationary collision could easily replicate. Still, the multiverse idea lingered, a reminder that the observable universe might be only a single frame in a much larger cosmic reel. A bench chair, second explanation reached further back, into the earliest instance after the Big Bang, the cosmic texture or topological defect. Moments after the universe ignited, the fundamental forces began to separate, gravity diverging first, then the strong nuclear force, and later the electroweak interaction. These separations were symmetry-breaking events, transitions in the cosmic fabric akin to the cooling of a liquid into a crystal. And like crystals forming in a turbulent flow, defects could emerge, cosmic strings, monopoles, domain walls. Textures, cosmic textures in particular, were predicted to produce distortions in the CMB, localized gradients where space-time had twisted and unwound. These signatures were rare, singular, and perhaps incredibly ancient. For a time, some cosmologists argued the anomaly matched this model, a relic of a symmetry-breaking event. Older than matter, older than light, older than the universe's transparency, yet textures should fade with cosmic expansion. They should weaken, not strengthen. And the anomaly's subtle evolution, its sharpening, its gravitational perturbation, resisted the static nature of a topological relic. Nor did any texture model explain the strange polarization behavior seen in the data. Still, the idea tugged at the imagination, a wound left from the universe's first moments. Refusing to heal, Beyond textures lay a theory both elegant and unsettling: the pre-Big Bang imprint, hinted at within Penrose's conformal cyclic cosmology. In this framework, the universe does not begin once. It begins endlessly. Each cosmic eon ends as entropy dilutes matter into radiation, leaving a smooth, cold universe that can be mathematically rescued into the next Big Bang. The transition is not a destruction but a transformation. Under this model, information could leak from one eon into the next, gravitational waves from supermassive black holes evaporating near the end of a previous universe could transfer faint signatures into the early moments of ours. Penrose suggested such imprints would appear as low-variance circles or rings in the CMB, quiet regions where energy once flowed from events predating everything we know. Some researchers who examined the anomaly found hints of this ring-like structure, but the anomaly was too irregular, too asymmetrical, too flexible in shape to neatly match the theoretical predictions. Even so, the possibility hung over the debate like a shadow that the anomaly might be a message from a universe long gone. Another theory looked not backward in time, but outward in scale: dark flow or hidden superstructure. In 2008, galaxy clusters appeared to drift at unusually high velocities toward a region of the sky, a phenomenon dubbed dark flow. Though later analyzers questioned its statistical significance, the idea remained compelling. What if an immense mass existed beyond the observable universe, pulling galaxies toward it through a gravitational influence that could cross the cosmic horizon? This anomaly deepened that question. Its gravitational lensing effect, subtle but persistent, behaved as if some invisible mass on unimaginable scales tugged at spacetime, warping the CMB's delicate structure. If such a superstructure existed beyond the observable boundary, its pull could create exactly the kind of distortions mapped by Planck. Yet here too, the theory met limits. A hidden mass could bend space, but it could not explain the low-frequency modulations in polarization, nor the feature's slight evolution. Gravity alone could not create the delicate harmonic patterns seen in the filtered data. Still, the notion remained haunting: an unseen continent of matter, older and larger than any cosmic structure, pressing its weight against the edge of our cosmic island. A more exotic idea emerged from high-energy physics: the false vacuum boundary. In quantum field theory, the vacuum is not empty. It is a seething ocean of fields, each with its own energy state. Our universe is believed to reside in a stable or metastable vacuum, but not necessarily the lowest possible one. Inflation itself may have begun in a higher energy vacuum that decayed into the one we inhabit. If a pocket of higher energy vacuum still existed beyond our observable universe, a region where the cosmic field had not fully transitioned, its boundary could imprint itself onto the CMB, the anomaly's shape, its faint gravitational pull. Even its evolving contours could match predictions of vacuum domain walls, but such walls would imply something profound: that our universe is expanding into, or retreating from, a region of space-time governed by different laws of physics. A frontier where constant shift, particles behave differently, or symmetries break in unfamiliar ways. This theory did not merely bend the edges of cosmology. It threatened to redraft them entirely. Finally, there was the most abstract idea of all: the quantum field echo. At the smallest scales, reality is ruled by quantum fields, omnipresent entities that vibrate, ripple, and fluctuate. During inflation, these fluctuations were stretched into the seeds of galaxies. But some theorists suggested that certain low-frequency quantum modes could have originated earlier from a pre-inflationary epoch, or from a phase transition in the primordial vacuum. If such modes survived inflation, they could leave resonant fingerprints in the CMB, a slow oscillation, a soft modulation, a faint echo of an older quantum landscape. The anomaly's rhythmic behavior, its sensitivity to filtering scales, its subtle shift over time, all hinted at a resonance deeper than classical physics could describe. Yet this explanation raised a troubling question. If the anomaly was a quantum echo, then the universe carried a memory older than the horizon itself, a memory that should not exist. Encoded in a radiation field supposedly frozen for 13.8 billion years. Each theory explained fragments of the mystery. None explained all of it. The multiverse offered collisions without contours. Textures offered relics without evolution. Conformal eons offered rings without gravitational pull. Superstructures offered mass without polarization twists. Vacuum boundaries offered influence without resonance. Quantum echoes offered resonance without shape. In every model, something remained unaccounted for, an element that refused to fit into any cage of mathematics. And as cosmologists moved deeper into the puzzle, a realization began to crystallize in the silence between debates. This anomaly was not merely a flaw in data or an artifact of interpretation. It was a signpost, a boundary, a whisper from the deepest architecture of the Fae cosmos. Something ancient had written itself into the universe's first light, and across decades of observation, it had waited, patient as gravity, silent as cold, for the moment when humanity would finally learn to read it. As the anomaly deepened, the universe seemed to draw its breath. What had once been a faint irregularity in the cosmic microwave background was now a frontier, a boundary of knowledge demanding new tools, sharper eyes, and quieter instruments capable of listening to the oldest vibrations in existence. Across mountaintops, deserts, frozen plateaus, and orbits far above the Earth, next-generation missions began to gather around a single question: what, exactly, was hiding behind the cosmic background? The first wave of hope came from the sky itself, from satellites designed to observe the universe with unprecedented precision. Among them was Light BRD, a mission crafted by the Japanese Space Agency in collaboration with international partners. Its purpose was simple yet monumental: to measure the polarization of the CMB with exquisite sensitivity, searching for the faint swirling B-modes imprinted by primordial gravitational waves. These waves, if they existed in the patterns predicted, could reveal whether the anomaly was tied to an early universe event, a cosmic defect, a vacuum boundary, or even the echo of a pre-inflationary landscape. Light BRD's detectors were designed to cool to fractions of a degree above absolute zero, reducing thermal noise until the instruments became sensitive enough to detect temperature differences smaller than 1/1,000,000th of a degree. In those delicate signals, scientists hoped to find clarity, a sharp signature that would either validate known physics or push them toward the uncharted. Further ahead on the scientific horizon stood CMBS-4, a sprawling network of detectors planned across the high plateaus of Chile and the icy expanse of Antarctica. Unlike satellites that drift in cold silence, these ground-based instruments would stare for years at the same patches of sky, building maps of unrivaled depth. Their goal was to measure the faint ripples in cosmic structure, induced by gravitational lensing, distortions that could reveal if something massive, something hidden, was tugging on the universe's earliest light. If the anomaly represented a superstructure beyond the cosmological horizon, its gravitational fingerprint would subtly shape the CMB lensing signal. CMBS-4's detectors, numbering in the hundreds of thousands, were built to expose that gravitational choreography in unprecedented detail. Parallel to these efforts was a concept still awaiting approval but fiercely anticipated in the scientific community: PICO, a mission proposal for a full-sky ultra-sensitive CMB observatory. If funded, PICO would turn the entire cosmos into a laboratory for understanding the anomaly. Its instruments promised polarization measurements 30 times more precise than Planck. With that precision, even the faintest whisper beneath the CMB would be uncovered or ruled out. But the search for answers was not confined to microwave light. The anomaly hinted at gravitational influences at depth, at motion, qualities that might express themselves through vibrations in space-time itself. This brought attention to a new class of observatories: gravitational wave detectors. The upcoming laser interferometer space antenna, LISA, would drift millions of kilometers from Earth, forming a triangular constellation capable of detecting gravitational waves far longer in wavelength than those observable by ground-based detectors like LIGO. These long waves could be relics of cosmic events that preceded the formation of light itself. If a boundary existed beyond the CMB, a bubble wall, a vacuum frontier, or a pre-Big Bang remnant, it might resonate in these low-frequency waves. Some models predicted that such a boundary could produce a continuous gravitational hum, a soft, persistent vibration threading through the cosmos. If LISA detected such a signature, and if that signal aligned directionally with the anomaly's coordinates, the implications would be unmistakable. Something beyond the CMB was exerting influence on the modern universe, on Earth. The search continued across landscapes chosen for their purity and silence. In the Atacama Desert, where the atmosphere thins into clarity, experiments like the Atacama Cosmology Telescope and its successors scanned the microwave sky with detectors shielded from water vapor and electromagnetic noise. Thousands of kilometers south, in Antarctica, telescopes embedded in the cold, dry plateau of the South Pole mapped polarization patterns with stability unmatched anywhere else on the planet. These observatories were uniquely positioned to confirm whether the anomaly was a genuine cosmological feature or an artifact of instrumentation. And with every passing year, the anomaly refused to fade. Instead, it sharpened, becoming more defined as tools improved. Yet the investigation extended beyond the CMB. If a massive structure lurked beyond the visible universe, its gravitational influence could subtly distort the arrangement of galaxies and clusters within the observable boundary. Thus, new missions turned their attention to the architecture of cosmic matter. The Euclid mission, launched by the European Space Agency, sought to chart the large-scale distribution of galaxies across billions of years of cosmic history. Its maps of dark matter, derived from weak gravitational lensing, could reveal asymmetric flows, unexplained accelerations, or directional anomalies that hinted at forces beyond the horizon. If these maps showed a preferential drift or distortion aligned with the CMB anomaly, It would strengthen the case for a hidden superstructure, the James Webb Space Telescope, JWST. Though not designed for cosmology at this scale, offered another pathway. Its deep field observations reached back to the earliest epochs of galaxy formation. If galaxies in certain regions appeared unusually stretched or displaced, if early structures formed faster or slower than predicted, these could be indirect effects of a deeper cosmic influence. Meanwhile, the forthcoming Vera C. Rubin Observatory prepared to scan the entire sky, night after night, in what would become the most detailed time-lapse of cosmic evolution ever created. Its sensitivity to transient phenomena might expose subtle distortions in the apparent motion of distant galaxies, gentle tugs, faint accelerations, or deviations too subtle for older instruments to notice. While these observatories searched the universe's visual and gravitational landscapes, a different kind of tool emerged from the smallest scales of physics: quantum sensors. Designed to detect minute fluctuations in spacetime itself, these devices relied on quantum coherence, the delicate alignment of atomic states, to sense vibrations that even gravitational wave detectors might miss. If the anomaly produced primordial gravitational noise, an echo of an earlier universe, quantum sensors could become the first instruments capable of hearing it. Yet even these tools were only part of the effort. In laboratories and data centers across the world, supercomputers ran vast simulations, digital universes evolving through millions of scenarios. Physicists attempted to model vacuum boundaries, multiverse collisions, cosmic textures, and exotic gravitational fields. They fed into the simulations every parameter the universe had revealed so far, testing which models could reproduce a signature even vaguely similar to the anomaly. Most failed. Some approximated fragments. None had produced a perfect match dot. As these tools advanced, the scientific tension grew sharper. On one side stood the possibility that the anomaly was a natural artifact, a rare statistical fluke, a misunderstood polarization artifact, or a quirk of data processing that would fade under deeper scrutiny. The history of cosmology contained many such phantoms, features that dissolved as instruments improved. But on the other side was a possibility far stranger: that the anomaly was not fading, that it was strengthening, that it was in some way evolving. Upcoming missions: Light BIRD, CMBS-4, Euclid, Rubin, LISA would soon converge upon the same region of space, each with a different language of observation: light, gravity, structure, resonance. If even two of these tools detected correlated features, the result would be undeniable. The universe, for the first time, would be offering a clue about what lies beyond the cosmic background. A message from a realm older than time. A whisper from behind the first light. And with every new instrument aimed toward the sky, the cosmos waited, poised on the edge of revelation as humanity prepared to confront whatever had begun to wake inside the oldest shadows of the universe. In the fading light of cosmic understanding, as theories stretch toward the edges of what can be spoken, a quiet question lingers in the space between data points. What if something existed before the universe itself? The thought moves like a cold current through the mind of cosmology, unsettling in its simplicity. A universe that remembers a presence older than its own beginning would be a universe shaped not merely by chance and expansion, but by inheritance. And in that inheritance, There may be traces of a story far deeper than the familiar chronology that starts with a blinding burst of primordial fire, the cosmic microwave. Background: the universe's earliest visible light becomes, under this lens, less a beginning and more an archive. Its faint warmth is not only the afterglow of a youthful cosmos cooling from its earliest moments. It may be the lingering imprint of an earlier era that brushed against a new reality forming in its wake. If a mark in that ancient radiation truly comes from before the Big Bang, then the familiar temporal boundary that separates before from after dissolves into something far more fluid. The universe becomes a chapter, not a book. A consequence, not an alternate cause. For decades, physics has treated the Big Bang as the ultimate line of demarcation, the moment where space, time, and every quantum field erupted into being. Yet theories such as conformal cyclic cosmology, pre-Big Bang string cosmology, and bouncing universe models whisper alternative possibilities. They suggest that cosmic histories may be layered, each universe leaving behind subtle fingerprints in the next. In these frameworks, the Big Bang does not mark the origin of all things, but instead a transitional pulse, a kind of renewal that transforms a previous cosmic state into a new unfolding. If so, the anomaly that scientists study with such care may be more than an irregularity. It may be a scar, a physical memory of an older universe, collapsing into the seed of this one. The emotional weight of such a suggestion is profound. A universe with predecessors is no longer alone. It becomes part of a lineage stretching backward into epochs that lie beyond measurable time, each with its own birth, evolution, and dissolution. A chain of existences, each one rising from the ashes of the last, and each leaving faint whispers embedded in the next generation's cosmic fabric. It is a vision both humbling and poetic, reality as a cosmic cycle, each universe leaving behind soft traces of its presence like ripples from a stone thrown into an endless ocean. This idea challenges the solitary comfort of a universe seen as singular and self-contained. For centuries, humanity has imagined the cosmos as a grand, isolated expanse, vast beyond comprehension but complete within itself. It offered a kind of existential clarity. Everything that exists within this one domain. Yet if a faint mark on the sky reveals another presence just beyond reach, a presence older, larger, or fundamentally different, then the universe begins to feel less like a final destination and more like a fragile membrane stretched across deeper, stranger waters. The possibility of a multiverse scratches at the edges of human imagination. It raises questions about identity, purpose, and the nature of reality itself. If this universe is not the only one, then life as known today becomes an expression of just one version of physical laws, one arrangement of particles, one fleeting configuration of matter. Countless others may exist with different constants, different dimensions, different histories. The anomaly, if it truly links to another universe, becomes the first hint that the cosmic isolation once assumed was never real. The silence humanity believed it inhabited may have always been shared. Yet there is a subtler, more haunting possibility. The universe may not simply have neighbors. It may have boundaries. Some theories suggest that the anomaly could be a contact point, a location where quantum fields from another region brush against the observable cosmos. Others imagine it as a gravitational shadow cast by a structure hidden beyond the cosmic horizon. And in more unsettling interpretations, The anomaly might be the signature of a false vacuum boundary, the frontier between the universe's current stable state and a deeper, more energetic vacuum that might lie beyond. If so, what has been detected is not merely a scar. It is a warning, a sign that the universe exists precariously within a larger field of potentials, any one of which could reshape everything. The philosophical implications ripple outward. What does it mean to inhabit a universe that may not be complete? One whose edges might conceal greater realities, or whose origin may be tied to cycles far older than the space it occupies. Humanity becomes, in this view, not central observers, but late-born listeners. Creatures who have arrived after almost everything important has already happened, attempting to reconstruct the earliest sentences of a story whose first pages have long been torn away. And yet, despite this disquieting possibility, there is a kind of quiet beauty in the role humanity now plays. The cosmos is not silent and never has been. It hums with the residue of ancient events, the whispers of collisions, expansions, and transformations. The anomaly, faint, elusive, and easily dismissed, is part of that chorus. It is a thread of uncertainty that might weave together the narratives of multiple universes into one tapestry of deeper truth. Science, in its most expansive form, becomes an act of listening. Telescopes, detectors, and simulations are instruments not only of measurement but of interpretation, tools to translate the universe's oldest murmurs into meaning. The search for answers becomes a quiet ritual, humanity reaching towards something that may not wish to be found, but which reveals itself all the same through subtle distortions in ancient light. If something truly exists behind the cosmic microwave background, something older, larger, or stranger, then the universe does not stand alone. It is part of a structure far more intricate than previously imagined. And in that realization lies both awe and unease. Awe, because existence becomes richer and more mysterious than any single universe could contain. Unease, because every discovery strips away another layer of certainty, revealing new questions that outrun the capacity to fully comprehend them. Perhaps the greatest mystery is not whether another universe left a mark on this one, but why the mark remains visible at all. Why does the cosmos allow such traces to persist through inflation, cooling, and the long drift of billions of years? What purpose does such endurance serve? Is it merely a quirk of physics, or is it the universe's own form of memory, a function of cosmic evolution that allows each cycle to carry forward echoes of the last? If so, then humanity stands at the threshold of an extraordinary moment. The anomaly, long regarded as a curiosity, now becomes a messenger. A quiet reminder that the universe has a past older than itself, a past that refuses to be erased. And as scientists prepare new missions and deeper analyses, the cosmos edges closer to revealing whatever it has hidden for so long. The documentary ends not with certainty, but with a slow descent into contemplation. The cosmic background, once considered the final horizon, pulses with a new tension. It carries the weight of something stirring behind it, something ancient and newly restless. The universe is no longer a silent expanse. It breathes, it remembers, and perhaps, in its own way, it speaks. And whatever is hiding behind that ancient wall of light is no longer silent. The universe may soon have to answer to what has awakened.